We're going to go over the first part of Chapter 2 today. So the topics for Chapter 2, classifying matter, states of matter, chemical and physical properties and changes. And after this, we'll take a look at Part 2. So Part 2 is really going to have the math in it. Part 1 will just be more objective material. Okay, so first of all, classification of matter, Section 2.1. Well, matter is anything that has mass and volume, as you can see here. It makes up all the stuff around us. In fact, everything in the universe can be either matter or its energy. And here the example is a brass pot, and you can see the copper and zinc atoms in it. This is a nice chart for classifying matter, and you can see that we can take matter and break it down first into pure substances and then into mixtures. And then each of these can be further subdivided. Pure substances can be broken into elements and compounds. And for our element, we have an example here, copper. That's the copper on the outside of a penny. And for the compound, we have water. And it's supposed to represent water molecules. On the mixture side, we can have homogeneous and heterogeneous mixtures. Our example for the homogeneous mixture would be brass, like we saw in the previous slide. And for the heterogeneous mixture, it's a glass of water with the pennies in it. Now, elements contain only one type of atom. And here are some examples: copper, lead, aluminum, oxygen. And here are the symbols. We'll be going over symbols in another chapter, but it's a good introduction now. You notice that each symbol can have either one or two letters, but the first letter is always capital, and if there is a second letter, it's always small. Now, don't worry about some of these letters, like you might look at lead and say, where do they get these from? We're going to see that's from a Latin name. Now, for compounds, we're going to see some examples. A compound contains two or more elements, and they're always in a definite ratio. And here is hydrogen peroxide, and you can see in the picture. The formula for hydrogen peroxide is H2O2. So that means that one molecule of hydrogen peroxide contains two hydrogen atoms and two oxygen atoms. So this ratio, 2 to 2, never changes for hydrogen peroxide. If you were to make the ratio any different, it'd be then a completely different compound. Table salt, the ratio is 1 sodium to 1 chlorine. And in sugar, we have a ratio of 12 carbon atoms to 22 hydrogen atoms to 11 oxygen atoms. And for water, we have just a 2 to 1 ratio. This is nice to compare hydrogen peroxide to water. You see they're same kind of elements, but because the ratio is different, all the properties are completely different. Now, table salt is a very common substance that's been around forever. In fact, it was so common, people used to trade in table salt, and in fact, actually use it for money. And we need salt to live. We can't live without it. So if you take a look at the salt in a salt shaker here, if you could see the individual particles, we would see alternating sodium and chlorine atoms here. Now, the sodium itself is a metal and looks like this. And the chlorine is actually a gas that has that pale green color. So you can see that when you combine these two together, if it was just a mixture, it would look like a combination of both. But a compound looks completely different than the elements that make it up, unless we have the sodium chloride. Now, both of these elements by themselves are very dangerous to be around, yet table salt is not at all. The mixtures, on the other hand, are two or more substances that are physically combined but not chemically combined. And these different combinations can have all different proportions of unlike compounds. So you can make a mixture of two things in all different proportions and it's still a mixture. And if we want to separate a mixture, we have to use physical means. And in this diagram, the physical mean that's being used here is filtration. So we have some filter paper in this funnel, and the person is pouring a mixture of a solid and a liquid into the filter paper. And the liquid passes through. You see the liquid here looks clear. And the color here, that orange color, is going to remain in the filter paper. Homogeneous mixtures, the composition is going to be uniform throughout. Now, uniform means that no matter where you would test your mixture, you get pretty much the same ratio of each substance by mass. So if we use brass as the example, if you were to take a knife and cut out a piece of brass in different places, and if you could figure out the amount of copper and zinc in each of those pieces, you'd see they'd relatively be in the same ratio. but it's a ratio by mass now. In a homogeneous mixture, homogeneous mixtures look like they're only one thing, and thus they can be confused with elements and compounds. If you look at milk, milk is a homogeneous mixture. Looks like it's just one thing, but it's made up of a lot of different things. Now, heterogeneous mixtures, on the other hand, are kind of obvious as being a mixture. You look at the example here. This is water and oil. You can see at least two different things in a heterogeneous mixture. And usually what you have is a non-uniform mixture. So in other words, whatever you would check, when you measure your mixture, you have different ratios of the substances listed. Think of like chocolate chip ice cream. You have the chocolate chips you can see, and the ice cream you can't. You can't see what's in it, but the number of chips you have in each bite is going to be different. All right, now it's time for a learning check. So what I'd like you to do is just take a piece of paper and identify each of these four things as a pure substance or a mixture. Now once you've done that, just click on the next slide and you'll see the answers. Okay, now for the answers. All right. So we see that pasta and tomato sauce is a mixture. Aluminum foil, pure substances, because that's going to be an element. Helium, pure substance, that's an element. And air is a mixture. Now here's another learning check for you to do. Can you classify these substances, these mixtures really, as homogeneous or heterogeneous? And again, you want to pause the slideshow here and write down your answers. Okay, here are the answers. So hot fudge sundae, heterogeneous mixture. Shampoo, homogeneous. Sugar and water, homogeneous. And peach pie, heterogeneous. Next, we're on to states of matter. Now we can have different states of matter. We can have solids, and solids have a definite shape. Definite means constant, so it's not changing. Definite volume, the volume won't change on you either. The particles are close together in a fixed arrangement. Many solids are like this, but not all. But yeah, the particles are very close together, that's for certain. Now you might think the particles don't move at all, but they do have some motion. The motion is more vibratory. So they more like vibrate in place rather than moving from one point to another. Liquids, on the other hand, have an indefinite shape, but a definite volume. So the shape of a liquid is just the shape of the container it's in. But the volume doesn't change. In the example here, they're pouring that blue liquid in. No matter what they pour it into, they're going to get the same volume. The particles are close together, like in a solid, but they're able to move around each other, so the particles are mobile. And again, they move slowly, but they move faster than that of a solid. Gases, on the other hand, have an indefinite shape. Gases always take the shape of the container they're in. They have an indefinite volume. They will expand to occupy whatever volume is available to it. That's why they fill their containers. And the particles are very far apart. You can see by the diagram here. So far apart you can squeeze them closer together. So gases are compressible. And the particles move very fast. They have a lot of kinetic energy. And here's an example of water and ice and water vapor, where we can see all the different phases at the same time. This is one of the few materials on this planet where we can experience all the phases at the same temperature. So look how we picture ice. A lot of space within the crystals of ice. Yet the water molecules are much closer together. So the water is then denser than the ice because of all that space. The water vapor, the particles leave further apart, so they're even less dense. Now that we start the properties of matter. Properties can be physical or chemical. This is an example of glass with water in it, and we see the water molecules in here. Now, physical properties are easily observed and measured without changing the identity of a substance. For instance, you could take the temperature of the water, just note that it's a liquid. And here are some other examples. Shape, physical state, boiling and freezing points, density, and color of the substance. These are all physical properties. Here's an example using copper. You might have some copper pots at home. Now, color, Copper was recognized by its color, that reddish-orange color. Now, it's shiny. It might get dulled if it's heated too much. It'll actually blacken a bit, but you can just take a piece of steel wool and shine it back up. Copper is a good conductor of heat and electricity. That's why we use it in wires. It's a solid at room temperature. Well, look at its melting point and its boiling point. Pretty high temperature to melt it. Forget about boiling it. Now, a physical change, on the other hand, is a little bit different than a physical property. A physical change occurs when the substance is in one state of matter and changes to another. So the change in the shape. So here's a bar of gold. So if you were to heat this gold and reach its melting point, it would then change shape, but it's still gold. Only might be liquid gold. There's no change in the identity of the composition of the substance in a physical change. The common examples of physical changes would be melting and boiling, freezing, condensing. Okay. Let's see some more here. Paper torn into two little pieces, that's a change of size. Gold hammered into thin sheets of gold leaf, change of shape. And water poured into a glass is also change of shape. So now it's time to take a little quiz and see how you're doing on this so far. So you want to stop the video and you want to classify these 5 changes as either a change of state or a change of shape. When you're ready, you can go to the next slide. So here are the solution. The first one, chopping a log into kindling, that would be a change of shape. Water boiling in a pot, change of state. Ice cream melting, change of state. Ice forming in a freezer, change of state. And cutting dough into strips, change of shape. Now, chemical properties and changes. Chemical properties describe the ability of a substance to interact with other substances. So many times a chemical property is easy to recognize because it'll mention 2 substances in the property. All right, chemical properties, when a substance undergoes a chemical change, there'll be a change in its properties as it becomes a new substance. So the original substance is turned into one or more new substances with new chemical and physical properties. So during a chemical change, a new substance that has formed has a new composition. That means its chemical makeup is different, and thus its chemical properties would be different, and also its physical properties. So the changes in all the properties. And here's the example they're using. Sugar caramelizing at a high temperature is an example of a chemical change. So you can put sugar on, I forget what kind of food this is, but I don't think I like it. Anyway, you can put sugar on top of this and heat it. And you'll see this done sometimes in a restaurant. They'll actually take a little blowtorch and they'll heat that, and the sugar almost starts to burn, but they want to just melt it. If you heat it too much, it will burn, it will blacken. And that would be an example of a chemical change. Now, we think of chemical changes sometimes not being reversible, but many of them are, but the ones we normally see around us are not. So even like making toast, the bread undergoes a chemical change. You can't get the bread back by cooling off the toast. Here are some more examples of chemical changes. Silver tarnishes. It reacts with sulfur dioxide in the air, and it becomes black. Wood burning. I mentioned about making the toast. You're not burning the bread when you do it, but it's a little similar. So wood burning, obviously we get our products look different. There's ash. You don't see this carbon dioxide, the water vapor. You obviously can experience the heat. You notice there's a change in mass, it seems also. That's because we've lost the CO2 and water vapor to the air. Iron rusting. An iron nail combines with oxygen under the influence of water to form orange-red rust. And it's hard to reverse that process, although it can be done. All right, now it's time for a learning check. Identify these properties as physical or chemical. So you want to stop and write down your answers, and then go to the next slide when you're ready. So just pause this now. Okay, on to the next slide. And our solution. So ice melts in the sun, that's physical. The key word here is not ice, but it's the melting part. So the verb is going to identify for us if it's a physical change. Copper is a shiny metal. That's a physical property. Paper can burn. That's a chemical property. Now, I want you to notice the difference between the properties and changes. The ability of paper to burn is a chemical property. The actual burning of the paper is the chemical change. A silver knife can tarnish. That will be a chemical property. A magnet removes iron particles from a mixture. That's a physical property. All right, now let's try another learning check. Classify each of the following as chemical or physical changes. So you want to pause for a second, write down your answers on a piece of paper. Then we'll go to the next slide and see the answers. Okay, here we go. The solution then, burning of a candle, that's a chemical change. And what you're looking for is the fact that the candle produces heat or light. That's the evidence that we need. Ice melting on the street, that's a physical change. The verb melting tells you that. Toasting a marshmallow, that's a chemical change. And toasting is like burning. Cutting a pizza, that's a physical change. Iron rusting, we had that earlier, so that's like an easy one. That's a chemical change. And that's the end of part 1.